What if everything you thought you knew about time was only half the story? Picture standing on a distant planet where clocks tick backward, where sunsets happen before sunrises, and where aging might reverse itself like some cosmic magic trick. The universe doesn't play by our earthly rules. Time bends, warps, and even shatters into fragments we can barely comprehend. Right now, somewhere in the cosmos, black holes are stretching seconds into centuries, and entire galaxies are trapped in moments that never seem to end. And here's the strangest part: you're caught in this dance too, hurtling through time's invisible currents with every breath you take. Think about it. We measure our lives in minutes and years, yet time itself is far more mysterious than any clock could ever capture. It speeds up when you're falling into a black hole's grip. It slows down when you're racing through space at near light speed. Some physicists even argue that time might not truly exist as we know it, that it's just an illusion woven into the fabric of our perception. So how do we make sense of something so fundamental yet so utterly bizarre? That's where the real adventure begins. Today, we're diving headfirst into the enigma of time across the cosmos, unraveling 30 mind-bending facts that will shake your understanding of reality. From planets where a day lasts longer than a year to the haunting possibility of parallel timelines brushing against our own, we'll explore the universe's strangest secrets. This isn't just a journey through science, it's a voyage into the very heart of existence, where every discovery pulls back another layer of the cosmic curtain. So buckle up. By the end of this, you'll never look at a ticking clock the same way again. Imagine watching a clock inch closer to a black hole's edge, each tick stretching longer than the last until seconds crawl like years. This isn't science fiction. Einstein's theory of relativity reveals that time doesn't flow at the same speed everywhere. Near a black hole where gravity twists space-time into a cosmic whirlpool, time slows to a near standstill from an outsider's perspective. If you could hover just outside the event horizon, your watch would barely move while clocks on Earth raced ahead. The film Interstellar brought this chilling reality to life with its astronauts stranded near a supermassive black hole. For every hour he spent on that watery planet, 7 years passed back home. His daughter grew old while he barely aged a day. That's the haunting power of time dilation. Gravity doesn't just bend light, it warps time itself. But here's what makes this even stranger. You don't feel time slowing down. To someone falling into a black hole, everything seems normal. Their heartbeat stays steady. Their thoughts flow at the same speed. It's only when they look outward, comparing their experience to the distant universe, that reality fractures. This paradox lies at the heart of relativity. Time isn't universal. It's personal, shaped by where you are and how fast you're moving. Scientists have even measured this effect on Earth. Atomic clocks on airplanes tick slightly slower than those on the ground, just billionths of a second, but proof that gravity and speed rewrite time's rules. Now scale that up to a black hole's crushing grip, and you get a cosmic funhouse mirror where time stretches beyond recognition. So next time you glance at a clock, remember, it's not just counting seconds. It's telling your story in a universe where time is anything but constant. What if you could step on a cosmic gas pedal and accelerate until time itself screeched to a halt? At light speed, the universe plays a cruel joke. Your watch stops ticking entirely. While Earth's clocks spin forward through decades, you'd experience no time passing at all. This mind-bending prediction comes straight from Einstein's special relativity, where the mathematics of Lorentz transformations reveal time as a flexible currency traded for speed. Picture a photon streaking across space at 300,000 kilometers per second. From its perspective, if it had one, the instant it leaves a star's surface is the same moment it strikes your retina, even if that journey took centuries from our viewpoint. This is relativity's ultimate gut punch. Motion through space directly steals from time's ledger. The faster you go, the more time dilates until at light speed, the cosmic ledger shows 0 seconds spent. Astronauts on the International Space Station get a tiny taste of this effect. Zipping around Earth at 28,000 kilometers per hour, their clocks lose about 1 second every 6 months compared to ground stations. But ramp that speed up near light's impossible threshold, and entire generations could rise and fall during what feels like your afternoon commute. The catch: matter can't actually reach light speed. It would take infinite energy. Yet this speed limit reveals time's deepest secret. It's not some universal metronome, but a personal experience shaped by your motion. Two people moving at different speeds literally age out of sync, like characters in some cosmic time-warped drama. So next time you're stuck in traffic, consider this consolation: every crawl forward is a tiny rebellion against time's flow, proof that even our slowest movements whisper relativity's revolutionary truth. We think of time as something eternal, an endless river flowing from past to future. But what if I told you the universe has a birth certificate stamped 13.8 billion years ago? At the moment of the Big Bang, time itself flickered into existence along with space and matter. There was no before, because before requires time to measure it. This isn't just physics, it's a cosmic riddle that rewrites everything we assume about existence. Picture this: trying to ask what happened before the Big Bang is like asking what's north of the North Pole. The question loses all meaning because the framework for it didn't exist. Space-time wasn't stretched out like a canvas waiting for history to paint on it. It burst into being all at once, a fireball of creation where even the laws of physics as we know them briefly didn't apply. Philosophers have wrestled with this idea for centuries. St. Augustine, way back in the 4th century, argued that time was part of creation rather than something God existed within. Fast forward to today, and quantum physicists speculate that our universe might be one bubble in an endless froth of multiverses, each with its own separate timeline. But here's the twist: even if other universes exist, their clocks would bear no relation to ours. There now could be our distant past or a future we'll never see. This raises haunting questions about purpose and permanence. If time had a beginning, could it also have an end? Some models suggest a big freeze where entropy maxes out and all change stops, a cosmic finale where time loses all meaning because nothing happens anymore. Others propose cyclical universes, bouncing from bang to crunch in an endless loop. But through all these theories runs one unsettling thread: our human experience of time as this steady, reliable backdrop might be the universe's greatest illusion. Astronomers see echoes of time's birth in the cosmic microwave background, the afterglow of the Big Bang still detectable as faint static in radio telescopes. That ancient light is like the universe's first heartbeat, a timestamp from when time itself began ticking. So when you check your watch today, you're not just measuring hours, you're reading the latest page in a story that started when existence exploded into being, leaving us all swimming in the currents of a river that didn't always flow. Hold onto your clocks, because here's something surreal: your watch would tick completely differently on Mars. While Earth spins through a 24-hour day, the red planet takes just 37 minutes longer, making Martian days or sols eerily close to ours. But that's where the familiarity ends. A full trip around the Sun takes Mars nearly 687 Earth days, meaning you'd celebrate just half the birthdays you would back home. NASA rovers even operate on Mars time, with mission controllers living on shifted schedules to sync with the planet's sluggish calendar. Now leap over to Mercury, where time gets downright schizophrenic. The tiny planet whips around the Sun at breakneck speed, completing a year in just 88 Earth days, but spins so slowly on its axis that a single day lasts 59 times longer than ours. Picture this: sunrise to sunrise on Mercury stretches a mind-numbing 176 Earth days. You'd literally watch an entire season pass before the Sun returned to the same spot in the sky. And here's the kicker. Because of its lopsided orbit, the Sun appears to reverse course in Mercury's sky during certain points, making time feel like it's playing tricks on you. But Jupiter, that's where gravity cranks the weirdness to 11. The gas giant's crushing mass warps time so intensely that clocks on its hypothetical surface would run about 26 seconds slower per Earth year. Sure, that sounds small, but consider this. NASA Juno probe had to account for this exact distortion just to communicate accurately with Earth. Every second of delay in its signals had to be calculated to untangle Jupiter's time-bending grip. These aren't just celestial quirks, they're proof that time isn't some universal constant. It's a fluid, ever-changing experience sculpted by the gravitational fists of planets and the breakneck dances of orbits. So the next time you complain about a long day, remember, somewhere on Mercury the Sun hasn't moved in months, and on Jupiter your watch would slowly but surely fall out of sync with everyone back home. The universe doesn't just have different time zones, it rewrites time's very rules wherever you go. What if the past isn't gone and the future isn't waiting? What if every moment that ever was or will be exists right now, frozen in place like frames in a cosmic film reel? That's the spine-tingling premise of the block universe theory, where time isn't a river but a vast, unchanging sculpture. Physicists like Julian Barber argue that what we call time might just be a trick of human perception, our brains stitching together static slices of reality to create the illusion of motion. Think of it like flipping through a book. Each page exists simultaneously. The first chapter doesn't vanish when you reach the ending. In the block universe, your birth, this very moment, and your last breath all coexist eternally. Einstein hinted at this when he wrote, "The distinction between past, present, and future is only a stubbornly persistent illusion." His equations treat time as just another dimension, no different from length or width. From this God's eye view, the universe isn't unfolding, it simply is a four-dimensional tapestry where every event has its fixed coordinates. Here's where it gets eerie. If the block is real, free will starts to look like a mirage. Your choices would already be embedded in the structure of space-time, like a path pre-carved through a maze. Some philosophers push back, suggesting consciousness itself might be what gives time its flow, that without minds to observe it, the universe would be a timeless still life. Yet evidence creeps in from odd corners. Quantum experiments show particles seemingly deciding their state only when observed, as if reality waits for a viewer to collapse possibilities into moments. And entropy, the universe's march toward disorder, might be the engine behind our subjective sense of time's arrow. But in the block, even entropy is just another frozen feature, like wrinkles set forever in cosmic fabric. So why does time feel so real? Evolution likely hardwired us to experience it this way, a survival tool for creatures navigating a world of cause and effect. But peel back that instinct and you're left staring at a universe where every second is an artifact of perception, and the now you cling to is just one slice of an infinite, unchanging whole. The next time you watch astronauts floating aboard the International Space Station, you're actually looking at time travelers, just not the flashy DeLorean-riding kind. These orbital pioneers are slipping into the future at a rate imperceptible to human senses but measurable down to the nanosecond. Thanks to Einstein's special relativity, their blistering speed of 28,000 kilometers per hour means time flows slower for them compared to Earthbound observers. Here's how the math unfolds. After 6 months in orbit, an astronaut ages about 0.007 seconds less than those of us stuck on the surface. That might sound negligible until you scale it up. Scott Kelly, who spent 340 consecutive days in space, returned to Earth having time traveled approximately 0.013 seconds into humanity's future. Stretch that to a hypothetical 5-year mission, and you'd gain nearly a tenth of a second advantage over everyone else. But velocity isn't the only factor warping their clocks. Earth's weaker gravity at that altitude speeds time up slightly, counteracting some of the velocity effect. This gravitational tug of war between relativity's twin phenomena, special and general, creates a cosmic balancing act. GPS satellites have to account for this daily. Their clocks run faster in high orbit, and engineers program in corrections to prevent your maps from leading you into lakes. Now imagine pushing this principle to extremes. A spacecraft traveling at 90% light speed would make 1 year onboard equal to over 2 years back home. Reach 99.9%, and that ratio explodes every month for the crew becomes 22 Earth years. Colonists aboard such a ship could return to an Earth where their great-grandchildren are older than they are. While we lack the technology for such extreme time jumps today, the ISS proves the principle is rock solid. Every orbit is a tiny leap forward, a whisper from Einstein that the future isn't fixed, it's a destination waiting at the end of a fast enough journey. Ever notice how you can scramble an egg but never unscramble it? That irreversible mess holds the key to one of time's greatest mysteries, why it only marches forward. The second law of thermodynamics calls this entropy, a measure of chaos in the universe that always increases over time. Picture a glass shattering on the floor, a million fragments flying outward in perfect disorder. No matter how long you wait, those pieces won't spontaneously leap back into your hand as a whole. That's entropy in action, the invisible hand that gives time its arrow. This law isn't just about broken dishes, it's the reason we remember the past but not the future. Every thought in your brain, every beat of your heart relies on energy dispersing from orderly to disordered states. Stars burn out, mountains erode, even information degrades into noise, all because the universe relentlessly grinds toward maximum entropy. Physicist Arthur Eddington called it time's fingerprint, the one universal process that never reverses. But here's the twist: while entropy dictates time's direction, it doesn't explain why the early universe started with such unnervingly low entropy to begin with. The Big Bang delivered reality in a state of exquisite order, like a pristine deck of cards before the shuffle. Some theorists suggest alternate universes might have arrows pointing backward, where entropy decreases and glasses reassemble themselves. Others propose our observable universe is just one bubble in a vast multiverse where time's flow varies wildly. Yet for us, trapped in this pocket of space-time, the rule holds firm. Heat flows from hot to cold, smells disperse through a room, and living things age, never the reverse. Even black holes, those cosmic vacuum cleaners, obey entropy by growing their event horizons over time. The universe is a one-way street, and every second drags us further into disorder. So next time you drop a glass, don't just curse the mess, marvel at the physics that makes its destruction a tiny echo of time's irreversible symphony. Tick-tock, except what if the smooth flow of time is an illusion, and reality actually stutters forward in unimaginably tiny jumps? That's the radical idea behind Planck time, the smallest possible unit of time, lasting just 10 to the power of negative 43 seconds. To grasp how absurdly brief this is, consider that light, the fastest thing in the universe, can't even cross the length of a single atom in this sliver of duration. Some theories suggest time isn't a continuous river at all, but more like a cosmic flipbook, advancing frame by frame at this fundamental scale. Loop quantum gravity takes this further, painting spacetime as a woven fabric of finite threads. Imagine the universe as a vast digital screen, where even time has a pixel limit. No half-steps between Planck moments exist, just as you can't hover between two frames of a movie. This isn't just philosophical musing, it could solve glaring paradoxes in physics. Black holes, for instance, might avoid infinite densities because matter can't cram into spaces smaller than a Planck length in any single Planck instant. Yet here's the catch: we'll likely never directly observe this quantization. Probing such scales would require particle accelerators the size of galaxies. Still, the math hints at profound implications. If time is pixelated, then Zeno's ancient paradox, where an arrow never reaches its target because it must first cross half the remaining distance ad infinitum, gets a loophole. Motion becomes a series of quantum leaps, skipping past the infinite subdivisions. The eerie beauty of Planck time is how it mirrors quantum mechanics' discrete energy levels. Just as electrons jump between orbits without traversing the space between, perhaps reality itself operates on a cosmic ticker tape, advancing in indivisible clicks. This challenges Einstein's smooth spacetime continuum, suggesting the universe might run on a deeper, granular code, one where even time has a refresh rate. That smartphone in your pocket holds a secret. It's constantly being lied to by satellites, not out of malice, but because time itself runs faster in orbit than down here on Earth. GPS satellites zipping around our planet at 14,000 kilometers per hour face a bizarre temporal dilemma. Einstein's theories of relativity warp their clocks in opposite directions simultaneously. Their blistering speed makes time slow down slightly due to special relativity, while their higher altitude, where Earth's gravity weakens, makes time speed up thanks to general relativity. This creates a cosmic tug-of-war where the clocks on these satellites gain about 38 microseconds every single day compared to ground-based timekeepers. At first glance, 38 microseconds sounds trivial until you realize that light travels nearly 12 kilometers in that sliver of time. Uncorrected, this discrepancy would throw off your GPS position by about 12 kilometers per day. Suddenly, your turn left in 500 meters navigation prompt could send you crashing into a lake. To compensate, engineers build relativistic adjustments right into the satellite software, deliberately slowing their atomic clocks before launch so they tick in sync with Earth time once in orbit. Without this fix, global positioning systems would become useless within minutes. Here's the mind-bending part. This isn't theoretical. We've measured these effects with absurd precision. Atomic clocks flown on airplanes in the 1970s. The Hayfel-Keating experiment proved that even commercial jet speeds create measurable time dilation. But GPS networks take it further, baking relativity into their daily operations. Every time your phone pings a satellite for location data, it's relying on Einstein's 100-year-old equations to account for time's fluid nature. The implications stretch beyond navigation. Imagine future civilizations building networks around neutron stars where gravity is billions of times stronger than Earth. Their entire concept of time synchronization would make our GPS adjustments look like child's play. For now, these orbiting timekeepers serve as a humbling reminder. Even our most advanced technology must bow to spacetime's whims, stitching together a shared present across the warped fabric of the universe. Picture two identical twins saying goodbye. One straps into a rocket bound for the stars, the other stays planted on Earth. When the traveling twin returns after a high-speed voyage near light speed, something impossible happens. They're younger than their sibling. Not by days, but by decades. This is the twin paradox, a thought experiment that shreds our everyday intuition about time. Here's the twist that makes it not a real paradox. The twins don't experience symmetrical journeys. The Earth-bound twin stays in a single, unchanging inertial frame, no acceleration, no turns, just steady gravity. But the astronaut twin undergoes radical changes. Violent acceleration at launch, hairpin turns around distant stars, and bone-crushing deceleration to return home. These maneuvers switch the traveler's inertial reference frames, breaking the symmetry between the twins. Special relativity says clocks tick slower for objects in motion relative to an observer, but general relativity adds that acceleration itself warps time. The traveling twin's path isn't just longer in distance, it's fundamentally different in spacetime geometry. Visualize it like two hikers taking separate routes up a mountain. One walks a gentle, steady slope, the other scrambles up cliffs, doubles back through valleys, and finally reaches the summit exhausted. even if they cover the same horizontal distance, the second hiker's path is tortuously longer in elevation changes. Time dilation works similarly. The astronaut's jagged trajectory through space-time accumulates less elapsed time than the Earth twin's smooth path. The math holds up. At 87% light speed, 1 year onboard equals 2 Earth years. Push to 99.5%, and that ratio explodes every month for the traveler becomes a decade back home. Atomic clocks flown around the world have confirmed microscopic versions of this effect, but the full-blown scenario requires velocities we can't yet achieve. So why does it feel paradoxical? Our brains evolved in a slow, gravity-bound world where now feels universal. But relativity reveals time as a personal experience, threaded through with the stitches of motion and gravity. The returning astronaut didn't cheat death, they simply took a shortcut through spacetime's fabric, arriving in Earth's future having lived less of it. The true marvel isn't the age gap, but the universe's ruthless consistency. Time bends for everyone, but never in quite the same way. We think of time as a straight line, a single dimension stretching from past to future. But what if time is as multidimensional as space, with twists and turns we can't perceive? Some physicists argue that time might have hidden layers like a second dimension curling around the one we experience. Picture a sheet of paper. We only see its flat surface until someone folds it, revealing new angles. Stephen Hawking took this even further with his concept of imaginary time, where time behaves like a fourth spatial dimension, blending seamlessly with the fabric of the universe. This isn't just abstract musing. It could solve mysteries at the heart of quantum mechanics. Particles at the quantum level seem to defy classical logic, existing in multiple states until observed. If time had an extra dimension, it might explain how particles choose their state, perhaps by moving through a hidden temporal layer we can't detect. Imagine a maze where the walls shift depending on which direction you look. In 2D time, quantum particles might navigate similar complexities, appearing to teleport or entangle across distances. Even stranger is the idea that multiple time dimensions could allow for parallel causality. Events might ripple through more than one temporal axis, creating branching chains of cause and effect. Think of a river splitting into tributaries, each flows separately, yet all connect back to the same source. In a universe with two-dimensional time, the past could influence the present along multiple paths, making outcomes less fixed than they appear. Hawking's imaginary time, a mathematical construct where time becomes a spatial coordinate, offers another radical lens. In this framework, the Big Bang loses its singularity, smoothing into a rounded point like the Earth's North Pole. There's no before because imaginary time curves back on itself, eliminating boundaries. This could bridge the gap between quantum mechanics and general relativity, two theories currently at war over how time behaves at cosmic and microscopic scales. While we can't perceive these extra dimensions directly, their fingerprints might lurk in quantum experiments. Particles tunneling through seemingly impassable barriers or entangled pairs reacting instantaneously across light years could be whispers from time's hidden geometry. The universe, it seems, might be keeping secrets about time, not in its flow, but in its very shape. So the next time you check your watch, remember, those ticking seconds might be just one thread in a vast, knotted tapestry of time we're only beginning to untangle. The screen you're staring at right now, it's not actually now. Every image, every word exists in a tiny pocket of the past by the time it reaches your eyes. Light takes time to travel, even across short distances, meaning you're always seeing the world as it was, not as it is, that coffee cup on your desk. You're perceiving it roughly 1 nanosecond in arrears the time light needs to bounce off its surface and hit your retinas. Scale this up to cosmic distances and the illusion shatters completely. When you gaze at the sun, you're seeing it as it appeared 8 minutes ago. The light from Alpha Centauri, that's a 4-year-old postcard, the Andromeda Galaxy. A 2.5 million-year-old relic, but here's the real kicker: your brain is in on the deception. Electrical signals crawl along neurons at a glacial pace compared to light speed, about 100 meters per second. By the time visual data travels from your eyes to your visual cortex, processes into recognizable shapes, and gets time-stamped as the present, reality has moved on. Neuroscientists estimate this neural delay at around 80 milliseconds, meaning your conscious experience lags behind the physical world like a badly dubbed movie. This creates a bizarre existential quirk. Your now is actually a carefully constructed illusion, a best-guess reconstruction by your brain. To prove this, scientists have flashed lights in sync with beeps, but delayed the sound just enough that subjects swear the light flashed later than it actually did. Your brain backdates events to compensate for processing delays, stitching together a seamless fiction of simultaneity. Even touch isn't instantaneous. The sensation of your fingers tapping this screen takes milliseconds to reach your brain, slightly longer for your toes. Your nervous system compensates by slowing down faster signals to synchronize perceptions, like a cosmic film editor aligning audio and video tracks. Without this, you'd feel footsteps before hearing them, or see a ball hit before feeling the impact. The chilling implication: there is no universal present. Every observer, whether human, camera, or alien on a distant world, constructs their own slightly offset version of now. Two people standing side by side experience different slices of reality based on how their brains process stimuli. The present isn't a shared moment, it's a personal bubble, continuously updated and forever lagging behind the unstoppable march of causality. So the next time someone says, "Live in the moment," remember, the moment you're experiencing already belongs to the past. Your brain just convinces you otherwise to keep you from drowning in time's relentless current. A wormhole isn't just a shortcut through space, it could be a tunnel through time itself. Picture folding a piece of paper so two distant dots touch. That's how wormholes theoretically connect far-flung parts of the universe. But Einstein's equations suggest these cosmic shortcuts wouldn't just bridge locations, they'd link moments too. Fall into one end, and you might emerge centuries earlier or later, like stepping through a door where the threshold is stitched together with time. The math behind this is both elegant and unsettling. General relativity allows for traversable wormholes, hypothetical structures held open by exotic matter with negative energy. These wouldn't collapse instantly like black holes, but could in theory remain stable enough to traverse. Here's where time gets twisted. If one end of the wormhole accelerates to near light speed or sits near a black hole's crushing gravity, time dilation would kick in, causing the two mouths to desynchronize. Return the moving end to Earth, and you'd have a bridge not just between places but between eras. Enter the slower-aged mouth in 2050, and you might step out the other side in 1980. The catch: stabilizing a wormhole requires materials that may not exist, substances with repulsive gravity to keep the tunnel from snapping shut. Even if we found them, the energy demands could dwarf a star's output. And then there's the grandfather paradox. If you traveled back and prevented your own birth, would the wormhole unravel? Some physicists propose quantum mechanics might enforce consistency, rerouting events to avoid contradictions. Others suggest parallel timelines branch off to absorb the chaos. Science fiction loves this idea, from Interstellar's tesseract to Contact's eerie vortex. But the real fascination lies in how close it skirts actual physics. Kip Thorne, the Nobel-winning physicist who advised Interstellar, calculated that a wormhole time machine could only access moments after its creation, no rewinding to dinosaur eras. You couldn't change what you hadn't already seen, yet this constraint hints at something profound. Time's flow might be more malleable than we thought, its rigidity just an illusion forged in the low-energy, slow-moving corners of the cosmos. So while wormholes remain hypothetical, their implications ripple through reality. They tease a universe where time isn't a one-way street, but a labyrinth with hidden passages waiting for someone bold enough to map its turns. The greatest surprise, the equations say it's possible. The universe may already be threaded with these temporal tunnels, woven into spacetime's fabric like seams we haven't learned to see. Right after the Big Bang, time didn't just flow. It oozed like molasses dripping through the fabric of reality. In those first unimaginable moments, the universe was so dense that a single teaspoon of space held more energy than all the stars we see today. Gravitational forces at this scale didn't just bend time. They nearly broke its rhythm, stretching seconds into what would feel like eternities under today's laws of physics. Here's what's wild. We can actually measure this slowdown in the cosmic microwave background, the afterglow of creation. The radiation patterns frozen in this ancient light reveal that atomic vibrations, nature's most precise clocks, oscillated slower in the early universe's crushing gravity. If you could somehow drop a modern atomic clock into that primordial soup, its ticks would drag compared to one left in today's thin, expanded cosmos. It's as if the universe itself was running in slow motion, weighed down by the sheer density of its own birth. This ties directly to cosmic inflation, that dizzying period when the universe ballooned from subatomic to cosmic size in less than a trillionth of a second. During inflation, spacetime stretched so violently that it effectively rewrote time's tempo. Picture a guitarist tightening a string, the tension rises, the pitch goes higher. In the early universe, gravity's tension was so extreme that time's pitch dropped to a deep, sluggish drone. Only as space expanded and matter thinned out could time finally speed up to the steady beat we know today. The implications haunt physicists. If time's rate wasn't constant, our cosmic calendar might need rewriting. Events we think took milliseconds post-Big Bang could have subjectively lasted far longer from the perspective of particles trapped in that soupy gravity. Even light from the first stars carries traces of this warped timeline, redshifted not just by expanding space but by the ghostly aftereffects of time's early crawl. So the next time you check your watch, remember, it's not just measuring hours, it's echoing a rhythm set 13.8 billion years ago, when the universe first fought to free time from gravity's vice-like grip. In a lab at Stanford, scientists watched as a qubit, a quantum particle acting as a computer's smallest unit, seemed to rewind its own state like a video played in reverse. This wasn't theoretical physics or a glitch in the system. In 2023, researchers demonstrated something that defies common sense. Under precise conditions, quantum systems can exhibit behavior indistinguishable from time flowing backward. Particles that had just scattered suddenly regrouped, probabilities that had branched collapsed back to their source. It's as if the quantum realm keeps a receipt for every transaction, allowing it to hit undo under the right circumstances. The secret lies in quantum mechanics' eerie flexibility. Unlike the macroscopic world where entropy dictates time's arrow, quantum systems can temporarily uncompute their states through a phenomenon called time reversal symmetry. Imagine tossing a deck of cards into the air classically, they'd scatter chaotically. But in the quantum version, there's a tiny chance every card could land back in the deck, perfectly ordered, as if the shuffle never happened. This isn't magic, it's mathematics. The equations governing particles at this scale don't care whether time runs forward or backward. To test this, physicists used quantum circuits to simulate particles interacting, then applied precisely tuned electromagnetic pulses to essentially rewind the system's evolution. The results were staggering. Qubits returned to prior states with 85% accuracy, as if causality had briefly flipped its script. But here's the catch: this reversal only works if the system remains perfectly isolated. The moment outside interference creeps in, the illusion shatters. It's like trying to rewind a movie while someone keeps changing the film reels. What makes this more than a laboratory curiosity is its implications for reality's fundamental nature. If tiny components of the universe can locally reverse time's flow, Does that mean time's arrow is less a universal law and more a statistical tendency? Some theorists suggest that quantum time reversal could explain mysterious phenomena like retrocausality, where future events seem to influence the past. Experiments with entangled particles already show that measurements made now can alter a partner particle's state in the past, a temporal paradox Einstein called spooky action at a distance. Yet this isn't a free pass for time travel. The reversibility is fragile, limited to infinitesimal durations and microscopic systems. You couldn't unscramble an egg or reverse your age using quantum tricks. But it does hint at a cosmos where time's rigidity is an emergent property of scale, something that solidifies as trillions of particles interact, but remains fluid in the quiet, solitary dance of the quantum world. So next time you watch a dropped glass shatter, remember, in some hidden corner of reality, a single shard might just be clicking back into place, rewinding the tape of its existence one fleeting quantum moment at a time. Time crystals sound like something ripped from a sci-fi novel matter that moves rhythmically without ever winding down, like a perpetual motion machine defying the laws of physics. But these aren't fantasy. In 2016, Nobel laureate Frank Wilczek proposed their existence, and by 2017, labs had created them. Unlike ordinary crystals where atoms arrange in repeating spatial patterns, time crystals exhibit structure in time. Their atoms oscillate in a fixed cycle without energy input, forever ticking like a clock that never needs winding. The secret lies in quantum entanglement and a phenomenon called time symmetry breaking. Normally, physical laws look the same whether time runs forward or backward. Drop a ball, and the motion makes sense played in reverse. But time crystals break this symmetry. Their components sink into predictable oscillations like a metronome that keeps perfect tempo even after you remove its battery. This isn't just weird. It's a whole new phase of matter joining solids, liquids, and gases on the periodic table of existence. Creating them requires chilling atoms near absolute zero and hitting them with precisely tuned laser pulses. The atoms then enter a quantum dance, flipping between states in a loop that resists entropy's usual decay. Google's Sycamore quantum processor even forged time crystals in 2021, where qubits cycled between configurations indefinitely, a breakthrough for quantum memory. What makes them revolutionary is their potential for quantum computing. Traditional systems lose coherence fast, their delicate quantum states collapsing like sandcastles in a tide. But time crystals' self-sustaining rhythms could anchor stable qubits, acting as fault-tolerant clocks for quantum operations. Imagine a computer that never drifts out of sync, where information pulses through circuits with the reliability of a heartbeat. Yet the wildest implication might be cosmological. If time crystals can exist indefinitely without energy, could the universe harbor natural versions? Some theorists speculate that exotic spacetime geometries or neutron star crusts might host these temporal oddities. It's a haunting thought that somewhere in the void, chunks of matter might be ticking silently, keeping time long after stars burn out. For now, time crystals remain lab-bound miracles, bending our understanding of time's grip on matter. They prove that even in physics, there are still doors left unopened, and behind one of them, a clock that never stops. What if time's steady flow is just an elaborate illusion, a shadow cast by something far stranger happening at the universe's edges? The holographic principle turns reality inside out, suggesting everything we experience, every ticking second, every swirling galaxy, might be a three-dimensional projection from a two-dimensional surface where time doesn't even exist. Imagine a movie playing on a screen. The actors move, time passes, but the pixels projecting them are static, frozen in a flat plane. In this radical view, our perception of time could be nothing more than a cosmic sleight of hand. The math behind this comes from black holes. When physicists calculated how information behaves at a black hole's event horizon, they stumbled onto something bizarre. all the data describing objects swallowed by the singularity seems encoded on its two-dimensional surface like a hologram's etched pattern. Stretch this idea across the cosmos, and the entire universe might operate the same way, with every event, every moment, stored as quantum bits on some distant boundary we can't see. Time in this framework isn't fundamental. It emerges from how those frozen bits interact when projected into our volumetric reality. Here's where it gets trippy. If the holographic principle holds, our linear experience of past, present, and future might be like the flickering frames of a film. The underlying real could be timeless, with causality and sequence arising only when the cosmic projector lights it up. Think of a vinyl record. The music unfolds over time as the needle moves, but the grooves themselves are static, holding the entire song at once. Similarly, the universe's true structure might encode all of history simultaneously, with our conscious experience scanning across it moment by moment. Experiments are already hunting for proof. Fermilab's holometer seeks microscopic jitters in spacetime that could reveal its pixelated, holographic nature. If detected, these quantum fluctuations would imply that time's smooth flow is an approximation, a collective effect of countless tiny, timeless bits. Even gravity, which shapes time's fabric, might not be a fundamental force but a side effect of this deeper holographic process. The implications rewrite existence. Free will, entropy, even aging could be emergent phenomena, like waves rising from an ocean whose depths never move. Some physicists speculate this might resolve contradictions between quantum mechanics and relativity by showing that spacetime, and time itself, isn't the foundation of reality but a holographic mirage. So the next time you check your watch, consider this. Those seconds slipping by might just be the universe's way of rendering a much weirder, timeless truth. Hollywood loves a good time warp moment. Picture the hero leaping through a wormhole or skimming a black hole's edge, only to blink and find decades have passed back home. But here's the reality check. Real-time dilation doesn't work like a light switch. It's not instant. It's not dramatic until you've spent serious hours bathing in extreme gravity or racing near light speed. Take Interstellar's water planet scene, where 1 hour equals 7 Earth years. The film gets partial credit. Those time jumps stem from the planet orbiting Gargantua, a supermassive black hole. But even there, the effect would require the crew to linger much longer in that gravitational nightmare for the timeline to skew so severely. Most sci-fi glosses over the grueling math. Time dilation is a slow burn, a cumulative effect that creeps up like compound interest. Imagine an astronaut circling a neutron star for a week. Back on Earth, maybe a month passes, not centuries. To achieve the jaw-dropping leaps seen in movies, you'd need velocities so close to light speed that the energy required would vaporize any known material. Or gravity so intense it would spaghettify you long before the clock noticeably slowed. Even Avengers Endgame's time heist plays fast and loose. Quantum tunnels don't just spit you into alternate years. You'd need to account for relativistic time differences between departure and arrival points. Real-world GPS satellites already do this, adjusting for microseconds of dilation. Scale that up to intergalactic travel, and the margins get wild. A 5-minute jump might land you years off course unless you've painstakingly calculated every curve in spacetime along your route. The truth is, time dilation isn't a narrative shortcut, it's a natural consequence of the universe's strict speed limit. Films compress it for drama, but the real magic lies in its subtlety. Those atomic clocks on jets, the Hayfel-Keating experiment, proved they tick nanoseconds slower than ground-based ones. It's a whisper of relativity, not a shout. So while Hollywood bends time like taffy, the cosmos operates on a stricter script. Warp time, but do it the hard way. Picture the universe's final act, not with a whimper but with a scream. The Big Rip isn't just an ending. It's a cosmic shredding machine where dark energy grows so powerful it doesn't just stretch space but tears the very fabric of reality apart atom by atom. Right now, dark energy is already accelerating the universe's expansion, pushing galaxies away from each other faster and faster. But in this nightmare scenario, it doesn't stop there. It escalates until the force overwhelms gravity, electromagnetism, even the nuclear bonds holding atoms together. Time wouldn't just slow down or stop. It would dissolve into chaos as the universe's clockwork unravels at the seams. The math behind this apocalypse is chilling. Most models assume dark energy's strength stays constant, but if it intensifies over time, a state called phantom energy, its push could become unstoppable. First, galaxies would vanish over the horizon, their light stretched beyond detection. Then, stars within our own Milky Way would drift into isolation, their warmth fading into the void. About 3 months before doomsday, Earth would detach from the sun's grip, hurled into darkness. In the final minutes, planets and moons would fracture as gravity lost its hold. Then, in the last milliseconds, atomic nuclei would shatter, protons ripped from neutrons, quarks torn from their partners. A cascade of dissolution leaving nothing but lonely particles too far apart to ever interact again. Here's where time loses all meaning. In a universe where no two particles can communicate, causality breaks down. No events can occur because nothing can influence anything else. No watches tick, no stars burn, no thoughts form, just an infinite, featureless void where before and after no longer apply. It's the ultimate entropy, not just heat death but structural annihilation. Yet this scenario hinges on dark energy's still mysterious nature. Current observations show it behaving like a cosmological constant, but even a slight deviation could tilt fate toward the Big Rip. Some theorists propose alternative endings, the Big Crunch where gravity reverses expansion, or the Big Freeze, a slow, cold fade, but the rip stands out for its violence. It's the only model where time itself doesn't just stop but is actively destroyed, its scaffolding ripped away like a stage collapsing mid-play. For now, the universe keeps expanding and dark energy remains enigmatic. But the Big Rip lingers as physics' most visceral reminder. Time isn't just a dimension, it's a privilege, one the universe could revoke in a final, unfathomable tantrum. Ever had a near-miss car accident where everything seemed to move in slow motion? That eerie stretching of time isn't just your imagination, it's your brain hijacking its own clock. When adrenaline floods your system, your perception of time distorts like taffy, stretching seconds into what feels like minutes. Neuroscientists call this phenomenon time dilation, and it's not some magical power, it's your amygdala kicking into overdrive, forcing your brain to record memories at higher resolution during moments of terror. Think of it like your mind switching from a standard camera to ultra-high-speed footage, cramming in extra frames of perception to help you survive. But flip the scenario. Sit through a dull meeting or wait in line at the DMV, and time contracts like a squeezed sponge. Hours evaporate into what feels like minutes, not because your brain shuts off, but because it stops bothering to timestamp mundane details. This boredom-induced time warp stems from something called the oddball effect. When your environment lacks novelty, your brain stops forming distinct memories, creating the illusion that less time has passed. Throw in something unexpected, a clown riding a unicycle through the office, and suddenly, time expands again as your brain scrambles to process the anomaly. The real kicker, neither version is accurate. Adrenaline doesn't actually slow time, it just tricks your brain into thinking it did by turbocharging memory formation. Studies using rapid-fire image tests prove this. People in high-stress situations don't perceive more actual visual data, they just recall more details afterward. Meanwhile, the oddball effect explains why vacations feel long in the moment but short in retrospect. Your brain compresses repetitive experiences like beach days into a single mental shorthand. while novel events like getting lost in a foreign city stretch out in memory. This flexibility isn't a bug, it's a feature. Evolution wired us to linger on potential threats and skim over monotony. The same mechanism that makes a falling rock seem to hover also lets us mentally fast forward through routine tasks. Even stranger, this subjective time isn't confined to your skull. Studies show animals experience it too. A fly's lightning-fast reflexes, its adrenaline-like chemicals make its world appear in slow motion compared to ours. So the next time you swear the microwave timer's broken, remember, it's not the universe messing with you. It's your brain, the ultimate timekeeper with a fickle sense of rhythm, constantly adjusting its tempo to the soundtrack of survival. Somewhere in the tangled equations of general relativity, there's a loophole that turns cause and effect into a Möbius strip, a world where events don't just precede or follow one another, but twist into infinite self-creating loops. Enter closed time-like curves, the ultimate cosmic paradox machines. These hypothetical pathways through space-time don't merely bend time's arrow, they tie it into knots, allowing particles or even people to travel back and interact with their own past. The math traces back to Kurt Gödel's rotating universe solution in 1949, where the entire cosmos spins like a vast carousel, dragging space-time into whirlpools that circle back on themselves. Picture this: you stumble into one of these curves near a rotating black hole. As you move forward, the twisted geometry of space yanks you backward through time, depositing you at your own starting point. But here's the twist: your arrival becomes the very event that sent you on the journey in the first place. No beginning, no end, just an ouroboros of existence where every effect is also its own cause. It's like writing a letter to your past self that says, "Burn this note," only to watch your younger hand obey, creating a loop where the instruction has no origin. Gödel's model isn't the only playground for these temporal acrobatics. Physicists have since discovered other solutions: Tipler cylinders, wormholes with specific alignments, even cosmic strings threading through space-time like needles through fabric that could forge these loops under precise conditions. The common thread: extreme rotation or gravity warping spacetime until the future direction bends to meet the past. In these regions, light cones, the pathway's causality can travel, tip so far sideways that they overlap with their own history. The implications unravel logic itself. A photon could complete a lap and collide with its younger version, interfering in a paradox-free cycle. More unsettling, you might meet your future self, whose warnings set you on the path to becoming them. The bootstrap paradox isn't just theoretical here, it's inevitable. There's no first iteration in a closed loop. Reality becomes a self-sustaining script where every line writes itself. Critics argue such curves would violate the second law of thermodynamics. How can entropy increase if the universe keeps replaying the same moments? Others suggest quantum effects might stabilize them, with probabilities aligning to prevent contradictions. Hawking proposed the chronology protection conjecture, a cosmic censorship that prevents time loops from forming, though no proof exists yet. For now, closed time-like curves remain scribbles in physicists' notebooks. But their existence, even hypothetically, forces us to confront time's deepest riddle. Is causality a fundamental law, or just an emergent property of the calm, flat spacetime we evolved in? Somewhere in the whirl of a rotating universe, the answer might be looping eternally, waiting for us to stumble upon it. When an electron spins in superposition, it's not just in two places at once, it's in two times at once. Quantum particles don't simply defy space, they shatter time's linear flow, existing in a ghostly limbo where before and after lose all meaning until the moment of observation collapses their possibilities into a single reality. This eerie suspension is more than a laboratory quirk. It's a silent revolt against time itself. Take Schrödinger's infamous cat trapped in a box with a quantum-triggered poison. Until you lift the lid, the cat isn't just alive and dead. It's frozen in a state where time hasn't yet decided which outcome gets to happen. The clock inside that box isn't ticking, it's paused, waiting for an observer to press play. This isn't hypothetical. Actual experiments with photons show they can delay choosing their path or even their moment of arrival until after they've supposedly already traveled. In a 2012 study, scientists demonstrated delayed choice quantum erasure, where particles seem to retroactively alter their behavior based on future measurements, as if time were a conversation where the ending changes the beginning. The implications are staggering. If quantum systems hover outside time until measured, does that mean time only emerges from observation? Some interpretations suggest reality is a vast tapestry of untriggered possibilities, where now is just the spotlight of consciousness illuminating one thread. Others argue entanglement, where particles instantly influence each other across vast distances, hints at a deeper, timeless layer beneath our temporal experience. Two electrons entangled at birth will mirror each other's spins instantly, whether they're a millimeter or a galaxy apart. Their connection doesn't crawl through time at light speed. It sidesteps time entirely, like secret notes passed outside the universe's clock. Even black holes, those notorious time warps, might rely on quantum timelessness. Hawking radiation, the energy leaking from their edges, requires particle pairs to pop in and out of existence at the event horizon. But in that fleeting quantum dance, time becomes irrelevant. The particles exist, annihilate, and tunnel through space-time without ever truly experiencing its flow. It's as if the universe keeps two sets of books, one for the orderly tick-tock we perceive, and another where time is just scribbled margin, notes in a ledger of probabilities. So the next time you check your watch, consider this. Those seconds might not be passing, they might be crystallizing, moment by moment, from a sea of timeless potential. The clock ticks not because time flows, but because we keep asking it what time it is. At the smallest scales imaginable, time might not exist at all, just a seething quantum foam where space-time itself flickers in and out of existence like static on a cosmic television screen. Theories like causal dynamical triangulation suggest that what we perceive as smooth, flowing time is actually a patchwork of microscopic quantum interactions, stitched together like pixels blending into a movie. Picture the universe as a vast, shifting network of tiny geometric shapes, tetrahedrons that snap together and apart in a frenzied dance, creating the illusion of continuity where there's really just chaos. In this view, time isn't fundamental. It's an emergent property like temperature arising from the jostling of atoms. The math behind this is mind-bending. Just as water's wetness doesn't come from individual H2O molecules but from their collective behavior, time might emerge from the way these quantum building blocks interact. Causal dynamical triangulation proposes that space-time isn't pre-existing. It crystallizes from these quantum events, with causality itself dictated by how the geometry connects. Think of it like a cosmic game of dominoes where each tile represents a tiny fragment of reality, and the chain of their falls creates the arrow of time we experience. Miss a connection and causality breaks, align them just right and time flows forward. Here's where it gets radical. If time is a byproduct of quantum interactions, then the Big Bang wasn't just the beginning of matter and energy. It was the moment when the universe first booted up its temporal operating system. Before that, there may have been no before, just a quantum soup where cause and effect hadn't yet taken shape. Some models even suggest that time could freeze or fracture in extreme conditions, like inside a black hole or during the universe's death throes, reverting to its primordial, pixelated state. Experiments are already hunting for clues. Scientists analyzing high-energy particle collisions hope to spot space-time's granularity, tiny deviations from smoothness that would betray its quantum origins. Others study cosmic microwave background anomalies, searching for fingerprints of a universe that once ran on a different kind of clock. The implications rewrite reality. If time is software, not hardware, then the flow we cherish might just be the universe's most convincing illusion, a shared hallucination woven from countless quantum threads. So the next time you glance at a clock, consider the possibility that those ticking seconds are really just echoes, ripples in a deeper, timeless sea where reality is still figuring itself out, one quantum connection at a time. The biggest question isn't where time began, it's what could have possibly existed before the beginning. If the Big Bang marked time's birth, then asking what caused it is like demanding a map of land north of the North Pole. The very word before loses meaning when time itself didn't exist. Yet human brains, wired for linear causality, revolt at this idea. We instinctively picture a cosmic egg sitting in some timeless void, waiting to crack open. But relativity paints a stranger picture. The Big Bang wasn't an explosion in space and time. It was the eruption of space and time. Theologians and physicists have collided over this paradox for centuries. St. Augustine argued in the 4th century that time was part of creation, a tool God fashioned rather than a stage he stood upon. Fast forward to today, and some multiverse theories propose a workaround. Our universe might be one bubble in an infinite froth of cosmic foam, each with its own Big Bang and timeline. In this view, before could refer to a meta-time governing the multiverse's expansion, a higher dimension where universes bud and wither like grapes on a vine. But even this kicks the can down the road. What created that timeless arena? Quantum gravity theories twist the knife further. Loop quantum cosmology suggests the Big Bang might have been a big bounce, where a prior universe collapsed before rebounding into ours. Here, time isn't born or destroyed. It cycles like a phoenix perpetually rising from its own ashes. But the equations reveal a haunting caveat. The bounce erases all traces of the prior universe. No memory, no causality, just an existential reset button. Then there's the downright eerie, no boundary proposal by Hawking and Hartle. They imagined the early universe as a 4-dimensional sphere like Earth's surface, but with time as one of the dimensions. Just as you can't point to a spot north of the North Pole, there's no point before the Big Bang. Time curves back on itself, seamless and self-contained. No creator, no multiverse, just a geometric inevitability where the universe is its own cause. Yet all these theories share a common thread. They force us to abandon everyday intuition. Whether it's gods, multiverses, or self-creating geometries, the origin of time remains the ultimate cosmic magic trick, a show where even the stage is part of the act. The deeper we dig, the clearer it becomes. Time's beginning might not just defy answers, but the very framework we use to question it. Flip a coin in deep space, and the physics dictating its spin would look identical whether you played the footage forward or backward. The same goes for colliding planets, orbiting electrons, even light bouncing off a mirror. The fundamental equations governing these events are perfectly symmetric in time. Newton's laws, Maxwell's electromagnetism, Einstein's relativity, none care if time runs forward or backward. Yet here's the cosmic joke. We never see shattered glasses leap back onto tables or scrambled eggs unscramble themselves. If physics is time-symmetric, why does reality feel so stubbornly one-directional? The culprit lies in the one law that does flinch at time reversal, the second law of thermodynamics. Entropy, the universe's relentless march toward disorder, is the only physical process that creates an unmistakable arrow of time. But here's the twist: entropy isn't a fundamental force. It's a statistical tendency emerging from countless particles arranging themselves into increasingly chaotic states. Imagine a deck of cards fresh from the factory, perfectly ordered. Shuffle it once and it's slightly disordered. Keep shuffling and the deck settles into randomness. Play that sequence backward and you'd see chaos magically reorganize into order, violating statistical norms. That's why time's arrow feels so obvious to us. We're watching the universe's endless shuffle in progress. Yet this raises a deeper puzzle. If entropy increases toward the future, why was it so unnervingly low in the past? The Big Bang delivered the universe in a state of exquisite order, like that pristine deck of cards. Some theorists argue this starting point isn't a coincidence. It's a clue that our universe is just one patch of a larger multiverse, where fluctuations occasionally spawn low entropy bubbles. Others propose that time itself might be symmetric on a cosmic scale, with entropy decreasing in a mirror universe on the other side of the Big Bang. Quantum mechanics adds another wrinkle. At microscopic scales, particles like electrons exhibit time-symmetric behavior, yet when entangled systems undergo decoherence interacting with their environment, they inherit entropy's arrow. It's as if time's asymmetry is contagious, spreading from the macroscopic world down to the quantum realm. Experiments with ultra-cold atoms show this in action. Isolated quantum systems can temporarily uncompute their entropy, but the moment they interact with the outside world, they fall in line with time's relentless flow. So why do we perceive this asymmetry so vividly? Evolution hardwired our brains to track cause and effect, a survival tool for creatures navigating a world where food doesn't unrot and predators don't unattack. But peel back that instinct and you're left staring at a universe where time's arrow might just be a trick of the statistical light, a shadow cast by entropy's slow climb from an improbable past to an inevitable future. The equations don't care which way time flows, we're the ones stuck counting the seconds. Your brain doesn't just perceive time, it manufactures it. Every memory, every anticipation, even the sensation of now, is a carefully constructed illusion stitched together by neurons firing in perfect orchestration. Neuroscientists call this the specious present, a 3-second window where your consciousness stitches sensory inputs into what feels like a seamless flow. But here's the unsettling truth: your brain doesn't process the world in real time. Visual signals arrive milliseconds slower than sounds, touch lags behind both, yet you experience them as simultaneous. Like a film editor splicing footage, your prefrontal cortex constantly backdates perceptions to create the fiction of a unified moment. This timekeeping isn't just about syncing senses, it might be the very foundation of selfhood. Patients with damage to the hippocampus, the brain's memory hub, often lose the ability to sequence events. They live in a fractured present, unable to string together past, present, and future into a coherent narrative. Without this temporal glue, even identity crumbles. Studies on meditation and psychedelics reveal how malleable this system truly is. When sensory inputs dim or neural patterns shift, time distorts dramatically, minutes stretch into eternities, or hours collapse into instants. The radical implication: time as we know it could be consciousness's user interface for reality, not reality itself. Philosopher Henry Bergson argued this over a century ago. What we call time is just our way of navigating duration, like a map simplifying a landscape. Quantum physics adds eerie weight to this idea. At microscopic scales, particles don't obey a tidy timeline. They hover in superposition until observed. Some interpretations suggest the universe only crystallizes into definite states when conscious observers force the issue, making time less a river and more a spotlight we sweep across potentialities. Even AI research mirrors this mystery. Neural networks process information in loops that eerily resemble our own brain's timekeeping circuits, yet they lack any subjective sense of duration. The difference might be biological urgency. Evolution wired us to track time because survival depended on predicting futures, when fruit would ripen, when predators might strike. In this view, time isn't woven into the cosmos but projected onto it by minds desperate to impose order on chaos. So the next time you check your watch, remember, those ticking seconds might be less about the universe's rhythm and more about your brain's desperate, beautiful attempt to make sense of a reality far stranger than it seems. What if every joy, every heartbreak, every breath you've taken has already happened countless times before, and will happen again endlessly in perfect repetition? Friedrich Nietzsche's eternal return isn't just philosophy, it's a cosmic horror story wrapped in poetry. He imagined time as a wheel spinning through identical cycles where you relive your life down to the most insignificant detail. The same coffee spilled, the same laughter shared, the same regrets endured. Forever, this wasn't metaphor to Nietzsche, it was a thought experiment meant to shock us into living authentically. If every choice echoes eternally, wouldn't you make sure it's one you could bear repeating? Fast forward to modern cosmology, and the eerie echoes of Nietzsche's nightmare resurface in Roger Penrose's conformal cyclic cosmology. This isn't mysticism, it's hard math. Penrose theorizes that the universe doesn't end in heat death or a big crunch, but in a state so stretched and empty that it becomes mathematically identical to the Big Bang's starting conditions. Time loses all meaning as particles lose mass, distances blur to zero, and the universe forgets its own scale. In this reset, a new Big Bang erupts not from nothing but from the ashes of the previous cycle. The kicker: information might carry over through these resets via Hawking radiation, imprints in the cosmic microwave background, creating a form of cosmic déjà vu where constants and laws reboot slightly altered each time. The contrasts are as stark as they are haunting. Nietzsche's cycle is rigid, a cosmic Groundhog Day of identical repetitions driven by metaphysical necessity. Penrose's is fluid, a rebirth with variations where black holes from a prior universe might seed structures in the next. One demands perfect recurrence, the other allows for evolution across cycles. Yet both share a chilling implication. Time might not have a true beginning or end, just an endless loop where every universe is both ancestor and descendant to itself. For Nietzsche, eternal return was a psychological hammer. For Penrose, it's a possible feature of Einstein's equations. But the spine-tingling question remains: if the universe does cycle, could traces of past iterations linger? Some researchers claim to have found concentric rings in the cosmic microwave background, potential bruises from collisions with a pre-Big Bang universe. Others argue quantum fluctuations might carry fingerprints across resets. If true, time's arrow might not point forward. It could curve back on itself in a spiral, with each turn rewriting the definition of now. Whether poetic or physical, the eternal return forces us to confront time's most unsettling possibility, that our stories aren't just fleeting but recurring scripts in a play without final act. The universe might not be marching toward an ending, just rehearsing for its next beginning. Could time exist without change, without ticking clocks, orbiting planets, or even the faintest vibration of atoms? Strip away all motion, all events, and would time still flow like an invisible river, or would it vanish like a forgotten dream? This question split two of history's greatest minds, Isaac Newton and Gottfried Leibniz. Newton saw time as absolute, a relentless, universal backdrop against which events play out, like an invisible stage that exists even when no actors tread its boards. To him, time was real and independent, a cosmic metronome that would keep ticking in an empty, frozen universe. But Leibniz fired back with a radical alternative. Time isn't a thing in itself, just a way we describe relationships between events. No change, no time. It's like asking about the grin of the Cheshire Cat. If the cat itself vanished, the grin can't linger without the face. Picture a universe locked in perfect stasis, every atom frozen, every photon suspended mid-flight. Newton's absolute time insists seconds still pass in this eerie stillness, that an unseen clock counts eternally in the void. But Leibniz's relational time scoffs at the idea. Without before and after, without cause and effect, what meaning could time possibly hold? It's like claiming a blank sheet of paper has invisible writing just because you believe in letters. Modern physics leans toward Leibniz. Einstein's relativity fused time and space into a dynamic fabric shaped by matter and energy. No events, no motion. Then space-time isn't just empty, it's undefined, like a blank DVD with nothing to play. Yet the debate isn't settled. quantum gravity theories hint at something stranger. In loop quantum cosmology, time dissolves into discrete jumps at the universe's smallest scales. Near the Big Bang singularity, some models suggest time might have evaporated entirely, leaving only timeless quantum equations. Even black holes stretch this paradox to the breaking point. At their cores, where gravity crushes reality into a point of infinite density, time may cease to flow altogether, not slow, not stop, but become as meaningless as north of the North Pole. The haunting implication: time might not be a stage or a river, but a shadow cast by deeper physics we've yet to uncover. Like a rainbow that vanishes when you change perspective, time could be an emergent illusion, a side effect of how we stitch together a universe of ceaseless change. So the next time you check your watch, consider this. Those ticking seconds might not be measuring something fundamental, but something far more mysterious: the universe's restless need to become. The universe is winding down, and time itself is running out of steam. Heat death isn't a dramatic explosion or a violent collapse, it's the slow, quiet suffocation of all possibility. Picture a room where every molecule of air has settled into perfect stillness, where no breeze will ever stir again. That's the future of the cosmos, a state of maximum entropy where energy has spread so thin, so evenly, that nothing can ever happen again. Stars burn out, black holes evaporate, even the last flickers of light fade into an endless, uniform darkness. Time doesn't stop, it just ceases to mean anything, because without change, without difference, there's no before or after left to measure. Think about a clock in a frozen void. Its hands might still move, but if everything around it is unchanging, no sunrise, no orbiting planets, no heartbeat, does its ticking still mark the passage of time, or is it just an empty gesture? That's the paradox of heat death. The equations of physics don't forbid time from continuing, but they strip it of all purpose. It's like a movie reel spinning long after the film has dissolved into white noise. The numbers behind this apocalypse are staggeringly vast. Current models suggest it could take 10 to the power of 100 years, a 1 followed by 100 zeros, for the last black holes to vanish into Hawking radiation. Beyond that, protons themselves might decay, dissolving matter into a faint mist of subatomic particles. Eventually, quantum fluctuations could spark rare, fleeting bursts of activity, phantom particles popping in and out of existence in the void. But even these would be so sparse, so insignificant, that they'd hardly register against the backdrop of eternity. Yet the strangest twist isn't the cold or the darkness, it's the way time unravels. Without events to mark its passage, causality itself dissolves. No cause leads to an effect. No story has a beginning or end. In a universe where every point is identical, where no energy can be harnessed to perform work, future becomes indistinguishable from past. Philosophers call this the end of time, but that's misleading. It's more like time becomes a runway stretching into nothingness with no plane left to take off or land. Some theorists offer a sliver of hope, or perhaps a deeper terror. In an infinite universe, quantum randomness might eventually spawn a new Big Bang, restarting the cosmic cycle. But even if that happens, the old timeline won't be revived. It will be a new story with new laws, new time. Our universe's clock, with all its trillions of years of history, will be lost forever, its final tick swallowed by the silence. So when you watch a sunset or feel the seconds slip by, remember, this isn't just time passing. It's time mattering, a precious phase in the universe's life when moments still have weight, when the arrow of time still points somewhere. Heat death reminds us that time isn't just a measurement, it's the canvas on which reality paints its story. And one day, the painting will be complete, the brushes dried, the colors faded to gray. The canvas will remain, but no one will be left to see it. You're a time traveler. Right this second, as you watch this video, you're hurtling into the future at the relentless speed of 1 second per second. It's the most underrated time machine in existence, your own life. Every breath you take, every blink, every heartbeat is a tiny leap forward through the fourth dimension, as unstoppable as a rocket blazing through space. We just never think of it that way because our brains are wired to see time as a backdrop, not a trajectory. Think about it like this: standing still isn't an option. Even if you froze in place, shutting out all movement, time would still drag you onward. Black holes can stretch seconds into centuries, and light-speed journeys can compress years into days, but no force in the universe can actually pause your forward momentum through time. You're always in motion, always arriving in futures you can't yet see. The real magic isn't in breaking this flow, but in realizing you've been riding it all along. Science fiction makes time travel seem about dialing up exotic destinations, dinosaurs, distant galaxies, the birth of stars. But the most profound voyage is the one happening invisibly in your bones. Aging is time travel, growth is time travel. The childhood photos on your phone, those aren't just memories, they're snapshots from ports of call you'll never revisit. The future you're barreling toward, it's not some far-off land. It's the next tick of your watch, the next sunrise, the next time you'll pause and realize how far you've already come. Einstein knew this when he fused space and time into a single entity, space-time. Just as you're always moving through space, whether walking down the street or sitting still on a spinning planet, you're always sliding through time too. Gravity can bend that path, velocity can twist it, but nothing severs it. Even astronauts on the ISS, gaining microseconds on Earth, aren't escaping time's flow, just dancing to its rhythm at a slightly different tempo. So here's the twist: you don't need a DeLorean or a wormhole to be a time traveler. You're already piloting the most exquisite time machine ever built, a human life ticking forward at the speed of existence. The only difference between you and a sci-fi hero is the direction. For now, the universe only sells one-way tickets, but the ride, it's been breathtaking since the moment you boarded. From black holes stretching seconds into centuries to quantum particles seemingly rewinding their own timelines, we've journeyed through a cosmos where time isn't just a ticking clock, it's pixelated, stretchy, and maybe even an illusion painted by our brains. Think about it. Astronauts slip microseconds into the future just by orbiting Earth. Ancient photons carry snapshots of a younger universe, and entire planets experience sunrises slower than their own orbits. The universe laughs at our simple ideas of past, present, and future, weaving time into loops, layers, and labyrinths we're only beginning to map. So, which fact shattered your reality? Was it the eerie possibility of closed time-like curves where cause and effect tie themselves in knots, or the cosmic horror of heat death where time becomes a runway to nowhere? Maybe the revelation that your own neurons are stitching together a fictional now from delayed sensory inputs. Drop your mind-blown reactions below. We're obsessed with these cosmic riddles too. And if you're hungry for more universe-shaking mysteries, hit subscribe. Next time, we might unravel parallel dimensions, dive into white holes, or crack open the Fermi paradox. The universe is stranger than fiction, and every discovery pulls back another layer of its secrets. Until then, keep looking up, and remember, every second you experience is a tiny rebellion against spacetime's wild, winding rules.